Brett is an architect. He runs his own firm, Brett Aylen Architecture, focusing on high-performance homes. Brett also happens to be the South Australian representative of the Australian Passive House Association as well. And in a certain way, we wanted to bring him. I really wanted to bring him in specifically on these discussions of the in-between of low-embodied carbon materials and also high-performance design, because Brett's actually had experience designing straw bale houses. He has designed earth-coupled houses. He's also designed a lot of the most thermally efficient homes in South Australia as well. So being able to understand how do we actually create a medium between a hybrid approach for high-performance homes that are net zero ready, that are also comfortable, and a fantastic investment as well. So if you can please join me in welcoming Brett.
So Ken asked me to speak at this one about air tightness and the devil in the detail. So yeah, quick introduction. I'm Brett Aylen. I run Brett Aylen Architecture. I've been designing energy efficient, comfortable, sustainable homes in South Australia for 20 odd years. I guess I grew up as a bit of a greenie, so I've got it in my blood. I remember as a kid going to green marches and save the whales and the environment, and so my approach to design is that it's fully integrated into the process. So air tightness in buildings is important for many reasons. We've talked about some of the technical stuff, we've talked about some of the natural materials. Here I'm talking about reducing heat loss, improving comfort, and importantly as well, protecting the building fabric. Just a bit of basics first on measuring air tightness, in case there's anybody in the audience who's not really familiar with that. So air tightness is measured using a blower-door fan. And there's a standard that suggests that you do it at 50 pascals of pressure, which is equivalent to a moderately windy day. So I think that's important because we're testing at a pressure that you get, commonly when you get some wind. And then it's expressed in air changes per hour. So the number of times per hour that the entire volume of the air inside the building is exchanged. So here's some air tightness testing equipment, blower door, looking from the inside and the outside, and that's on one of my projects. So the first project that I had blower door tested was in 2012, and it was the zero carbon house, and that was tested as part of the CSIRO study into air tightness of Australian homes. And interestingly, I had 2 houses tested that year, or rather when they did that very similar materials, same builder. The first one got an air change of about 12.5, and the second one is about 5.5, and really the only difference was timber frame windows versus PVC windows. So in that case, I was just at the beginning of my journey of understanding air tightness, but obviously the windows and doors are very important. This at the top there is the result of that house that was being tested. So that's the first time I've attempted to get a passive house standard house, and we managed it. So air changes of 0.6 in the passive house standard. Just a bit of a comparison there from different standards around the world. So in the construction code here, we're aiming for a minimum permeability of 10. In the UK, they've got a couple of different levels of practice, and then that CSIRO result suggested an average of 15.4 around Australia. However, I think it's probably worse than that in reality, because they tested a lot of architect design high-performance houses in that research. So look, the importance of air tightness in terms of heat loss. Assuming that a house is well designed with good insulation and minimal thermal bridging, then that graph demonstrates, the grey area in that graph demonstrates infiltration. So at 0.6 air changes per hour, you can see that there's not much contribution to the energy performance from air leakage, but at 10 air changes per hour, the energy consumption, in a sense, or leakage due to the air infiltration is as big as it is from the windows and the opaque elements. So all of a sudden, it becomes really important to control the air leakage. There's an interesting quote there from 475, which is a high-performance building supplier in the USA, that talks about air tightness can have 1/5 the energy loss where compared to the same insulated enclosure which is leaky. So that's just in words what I was demonstrating by that graph. So the takeaway there, air leakage equals energy leakage. And air tightness is also obviously very important for improving comfort. So we've all experienced a draft. So thermal comfort has got a lot to do with air movement. So controlling air leakage is going to be, you're going to feel that directly. So seal it tight and then ventilate it right is one of the principles here. And if you've got chills, you can put a door stopper in, but that's not really a very high-tech approach. So get it right with the fabric, as everyone's been saying. So whether you use membranes or other methods, get the air tightness right in the fabric. Lastly, of the good reasons to have air tightness is protecting the building fabric, and this is a really important one because if you've got a lot of air movement through the fabric, that air carries moisture with it, and if you don't have good vapor control layers, what you get is that airborne moisture. You get interstitial condensation, and therefore you potentially get mold and damage to materials. So it's really important for the fabric, the building fabric, and so the takeaway there is airtight buildings last longer. So how is air tightness achieved? Well, essentially, it's by reducing the infiltration, sometimes called uncontrolled ventilation, and there's various construction methods that you can do that with, as we've seen this evening. So plastering, hard plaster, for example, is one method. Fully taped membranes is one method. You can use wood board composites with well-joined surfaces. So there's a lot of different ways to do it. The importance is that it gets addressed. So quality workmanship and proper installation is really important. And then obviously not only the membranes themselves or the air barrier sort of materials, but also windows and doors are vitally important, as I demonstrated at the beginning there, timber versus UPVC. Timber can work, obviously, as long as it's been designed for the purpose. So how is it achieved? We need to start understanding control layers in a building. So, I'm using timber frame lightweight construction because that's what I design with and that's what's fairly common here. but these are principles apply, whatever the fabric. So essentially we've got the cladding that deflects the rain on the outside, and then we've got a water-resistant barrier, also called essentially a weather-tight barrier, so that next layer, and then a thermal control layer, so the insulation. Then we've got the air control layer and the vapor control layer, and they're drawn right next to each other because they're often one material if it's in a membrane, but they don't necessarily occur in a single material. So really the key takeaway principle here, in a sense, is that it should be continuous. If you have a drawing, you should be able to take a red pen, because red is often used for an air barrier layer, and draw a continuous line all the way around the envelope of the house. And if you can join that line all the way around without any breaks, there's a pretty good chance that you're going to have an airtight building. So, and it's primarily a planning task. So the planners have got to get that right. The planners have got to consider that. It's important that when we're designing buildings, we design them in such a way that it's easy to construct that airtightness layer. So, and then the next obvious principle there is the continuity of those control layers. So, it's relatively easy to do it on a flat surface, but it becomes really important when you get to junctions. And the idea there is that, especially the air and vapor layers are continuous. So when they join in a corner somewhere, you've got to make sure that you somehow continue it to the next surface. In terms of membranes, you essentially do that with high-performance tapes and sealers. So 6 key things to get right. Keep designs simple. You can imagine if you've got a complex architectural form, as much as I like designing complex architectural forms, they're quite hard to get the airtightness to work. If you've got lots of complex joins and angles, I think your builder and your tradies are going to be jumping up and down on site and going, bloody architect, bloody designer, Choose robust materials and don't substitute on site, because obviously if something's been designed to work a certain way, then it has to work that way. And if there's a substitution, we're talking about complex issues here. So hopefully the designers have looked at those complex issues and got it right. Think about junctions in 3D, very important. And then communicate all of this clearly through drawings, site meetings, workshops and the like. Put good site management in place and undertake leakage tests while the air barrier is still accessible. That's a really important one. So don't cover it up. Start doing the testing as early as possible. So really, airtightness is a team effort. That's probably the most important takeaway I can give, in a sense. You work with the technicians, you work with the designers, you work with the builders. Everyone's got to work together. So there's one of my details. We've got the blue dotted line on the outside is the weather tightness layer. We've got the red dotted line on the inside is the air tightness layer. I do, as a minimum, the houses that I design have the blue layer on the outside, so the weather tightness, which is of primary importance because you want to keep the building dry. You can get relatively good air tightness with a well-installed weather barrier layer. But if you want to go for the high performance of, down towards the passive house standard, then in a lightweight construction like this, you need the internal membrane as well. So there's great resources out there, just pointing out there that, those details have been worked out there in 3 dimensions and not only sketched in a 3-dimensional software package, but also then built in full-scale models. So there's a lot of good research out there and a lot of good suppliers that have these kind of details. So it's a matter of really getting your head into these details. So there's one of my projects. You can see there it's fully wrapped on the inside and the blower door test is underway, and you've got the whole team there. So you've got the builder, you've got myself, not in the photo, but you've got the owner, everyone working together to achieve that result. And it's important to have a building culture that goes with that. So, what that sign suggests is report all penetrations to the supervisor. So if you do something, fess up. Because yeah, we find when we do a blower tour test, you know, the builder's always running around with tape and sealant and kind of like, oh, you know, shit, there's a gap there, there's a gap there, there's a gap there. So if you know that in advance of when the test is going to be done, it makes it much easier. So thanks, everyone. The final takeaway there is that air tightness is good for everyone.